on module 3 of computer organization, in which we will be discussing about the interrupts and various types of interrupts, its hardware, along with the steps that has to be followed while saving and restoring the data in when the interrupt is enabled. Operations. So here what happens is, when the print or the output, that is n lines, are ready, one single output is ready, only then the printer or the print routine starts. Print routine will start. So in order to do that, the printer has to send the interrupt signal to the processor saying that it is free to print. So what happens is, the print routine will be restarted whenever the next set of n lines are available for printing. Whenever the next set of n lines are available for printing, the print routine will start. We have two routines. One is compute routine and the print routine. This is nothing but the instructions or the program. In general, we call it as program, or it is the set of instructions that has to be performed. So if compute takes longer time, if compute takes longer time to generate n lines, then the time required to print them, the processor will be performing useful computations all the time. Thereby, what happens is, the time required to execute the entire program will be reduced. So this computation as well as the printing will be completed parallelly. Thereby avoiding the wastage of resources. Here, when we say the wastage of resources, it is the processor time, which is more precious than any other device as far as the critical computations are required. For example, see, in case of some of the examples where it is very critical, in terms of safety devices like fire monitoring systems, there we have two routines. One is to check for fire, and one is what are the tasks that has to be performed when there is a fire. In case of fire monitoring system, yeah, what happens is, there will be the sensor deployed in the buildings, and these sensors will be idle if the conditions are normal. When there is a fire, these sensors will send the signal to the processor. These sensors or the fire sensors will send the signals to the processor. The processor in turn activates the devices that are used to control the fire. So here we have two routines. One is monitoring and one is execution. So here the interrupt plays a major role, because the fire will not occur all the time. The occurrence of this event is very less. The occurrence of this event is very less. So if it is done, if the programming is done using a polling method, each time the processor has to waste time roaming around here checking for these conditions. If it is in a polling method, other than the two method we follow is mainly the polling method and the interrupt method. So in case of interrupt method, only when there is a fire it will send the signal, and until then the processor need not check for any of the conditions of the sensors. Whereas in case of polling method, each time when it executes or completes one cycle, it has to check for the sensors. There is a lot of disadvantages of the polling method that we will discuss in our next coming slides. So the majority of the processor time can be used in performing some other applications, rather than wasting the time in checking for the particular event to occur. The advantage of interrupt is that the interrupt As soon as there is a fire, it will send the signal irrespective of the condition of the processor. The processor will stop the task, whatever it is performing, immediately, and it will switch over to the task that has to be performed when the fire is occurred. That is, it may be turning on the alarms, it may be turning on the motor pumps, or alerting some uh, agencies. All these things can be, the programs related to that can be written in this particular routine. This is how the processor time can be reduced. So in this particular slide, we will discuss about what are the steps that has to be followed when an interrupt occurs. So when an interrupt occurs, I said that the normal execution of the processor has to be stopped, and the priority or the instructions that correspond to that particular interrupt has to be executed. So in the example what we discussed earlier, that is the fire monitoring system, when the fire occurs, the processor will get the input or the interrupt from the sensor saying that there is a fire. At that moment, it has to execute the separate task that is written separately, that corresponds to extinguishing the fire. It may be by setting up the alarms. It may be by setting up, turning on the uh, extinguisher sprays or water pumps, or informing the agencies, whatever it may be. The instructions related to that are written separately, and that is called as interrupt service routine. That is called as interrupt interrupt service service routines. And in this interrupt service routines, these are written separately from the main program. These are always written separately from the main program. And there will be a main program, and there will be interrupt service routine, same as the subroutines. We had discussed in the subroutine that the main program is written somewhere, and after that the subroutines are written. Similarly here, there are fixed locations for each interrupt that is supported by the processor, and in that particular location you need to write the interrupt service routine. Interrupt service routine means the task that has to be performed when the interrupt occurs. In this example, what we are discussing, it is the task to extinguish the fire. What are the tasks that has to be performed to extinguish the fire? That has to be written in the interrupt service routine. That may be turning on the alarm, or informing the agencies. That all the related, for those tasks, the program has to be written separately, and that program is called as interrupt service routine. And these interrupt service routine have a fixed locations, whereas the subroutines will not have a fixed locations. So now the processor has to stop the normal program. It has to come to the service routine, execute this task, and go back. Same as the subroutines. In such cases, when an interrupt occurs, the current contents of the program counter has to be stored. This program counter will have the address that corresponds to the next location. That is current, if the current instruction, current address from where the instruction is being fetched is, for example, 10, then the PC will have the value 11, and this 11, from this is the location from where the program has to begin. In such cases, these PC values are stored in the temporary storage location, written from the interrupt instruction at the end. After executing all the instructions that corresponds to the task to extinguish the fire, in this example, after completing all those, it has to return back to the main program. When it returns back to the main program, it has to resume the execution of the program where it has stopped. For example, let me take as in the address 50. When the computer is executing the task that is present at the address location 50, let us assume that the interrupt has occurred. Then when it what it has to do is, it has to stop all the execution, it has to stop the execution, or it has to halt the execution at 50, go to the service routine, execute those tasks, and come back. Where should it come back? It should come back to the next location that is executed previously. So this address has to be saved. And when the return, when here there is two instructions, one is return and return from the interrupt. There is a return from interrupt instruction that is written in the service routines. Always the interrupt service routine will end with return from interrupt instruction. When it comes across return from the interrupt instruction, then the PC will be restored back to the pre the stored value of PC, that is temporarily stored when the interrupt service routine or when the interrupt occurred, will be restored back to the PC and the normal execution starts. In many processors, the return address is saved in the processor stacks. Alternatively, it may be saved in the special locations such as registers provided for this purpose. In some of the registers, in some of the processors, there is something called link register, same as the link register that is present in case of subroutines. We have a link register. Similar to that link register, there are registers that hold the return address. So this is how an interrupt process occurs. There is nothing much difference when we speak about the subroutines and the subroutines and the interrupt service routine. They both are same, but the interrupt service routines are always written will have a fixed memory location. In a when if we have a particular memory we are speaking about, then the address range to store the interrupt service routine is fixed. The address locations that store the interrupt service routine is fixed, whereas the subroutines, it starts immediately next to the main program. When the main program ends, the subroutine program starts. Or subroutines can be written anywhere in the program, and it has to be referenced using the label whenever it is required, or it has to be called using the address whenever it is required. This slide gives a clearer view of the interrupt, that is resemblance to the subroutines. Assume that the interrupt arrives during the execution of the instruction I. Here we have the instruction I. Let us assume that the interrupt occurs at this position. Now our question is, what is the instruction that has to be executed next? That is I plus 1, right? I plus 1. If the interrupt has not arrived after I, the instruction that is present in I plus 1 has to be executed. So now what happens, because the interrupt has occurred, the next instruction will not be executed, that is present, the instruction that is present in I plus 1 will not be executed. Instead, what it does is, here this I plus 1 value will be stored in some temporary register or temporary register or stack. This value that is present in I plus 1 will be stored, so that when it returns back, the execution will start or resume from this particular location, that is I plus 1, pointed by I plus 1. So since the interrupt has occurred, the control has to go to the interrupt service routine. So in the interrupt service routine, in this example, you will write the program that is used to print the print output. In order to print the output, there are some programs that has to be written. Without writing the program, it cannot display or it cannot print with the printer. So we need to write the instructions to print. Once the instruction is written, at the end of the program we will have a return from interrupt instruction that replaces the PC value by the address pointed by I plus 1, the address I plus 1. PC will at the when the processor executes the return instruction, the PC value gets automatically replaced by the value that is present in I plus 1. PC value will be replaced by the value I plus 1, that is the address. Now, once it comes back, it executes the normal execution. Same way as the subroutines, when a subroutine is called, we know that the program has to, the PC value will be stored, and then it will go to the subroutine, execute that, then return back to the next instruction, that is returns to the address that is pointed by the PC that is stored earlier before during the call of subroutine. So after the execution of interrupt service routine, the processor has to come back to the I plus 1 location. It has to come back to I plus 1 location and execute or resume the normal task until the next interrupt. Interrupt can arrive anywhere in the program. It is not fixed. Whereas the subroutines, the call for subroutine is fixed. Call for subroutine is fixed. At one stage, the subroutine has to be called if it is mentioned, but the interrupt need not be the location of the interrupt at which it arrives may not be fixed, is not fixed. So the clear difference between the subroutines and the interrupts will discuss in detail. Till now we treated that both the interrupt service routine and the subroutines as similar, but the major difference between the subroutine and interrupt is that the subroutine performs the function required by the program which it is called, because there is a dependency between the main program and the subprogram or subprogram also called as subroutine. There is a dependency. The task in the subroutine is a subprogram that is present in the main program that we will write separately. Whereas here in case of interrupt service routine, there is nothing to do with the program that is being currently executed, or the it doesn't depend on the program that is being executed currently. The situation will be entirely different when it comes to the interrupt. There are two different programs. When the interrupt occurs, the program will be different, and when there is no interrupt, the program is different. There is no link between the two programs. There is no link between the two programs. Only when the interrupt occurs, that particular task has to be performed. In such cases, it will be written in the interrupt service routine. It will execute only the task, only the instructions that are written in the interrupt service routine. It is not required for a interrupt service routine, the program in interrupt service routine and the program in the main program to be performing the similar task, but they are entirely different. The applications are entirely different as compared with the main program. In the way, the original program can continue execution without being affected in any way by the interruption except for the time delay. This slide we will be discussing about saving and restoring information when the interrupt occurs. We know that when the interrupt occurs, we need to share some of the information or some of the data that are present in some of the registers. So when, as we know, when the interrupt occurs, we need to switch over to the interrupt service routine, execute the interrupt service routine, and return back. There is a chances that you need to transfer some of the data from the main program to the in a service routine, or you may need some data from the interrupt service routine back to the main program. So the most of the modern processors save only the minimum amount of information needed to maintain the integrity of the program execution. So this is because the process of saving and restoring takes time. So this indirectly increases the interrupt latency. Interrupt latency means the time, say time the interrupt time it takes to respond to the interrupt. That means, see, let us assume that the interrupt has occurred, and there will be some delay between the occurrence of the time and the actual beginning of execution of interrupt. That is interrupt latency. Time taken to respond for the interrupt is nothing but the interrupt latency. That is time taken to respond to interrupt. Interrupt is called latency or interrupt latency. So this has to be minimum, because some of the applications will be very critical. All those the programs related to the critical applications are done using the interrupt. In such cases, the scope for interrupt latency is very minimal. So because since if the more data transfer takes place between the main program and the interrupt service routine, then there should be a lot of data that is to be transferred or restored from the register to the memory location. That adds up to the latency. So to avoid that, we need to minimize the number of data that has to be transferred from the main program to the interrupts. So here typically the processor saves only the two contents, that is the program counter and the program status word. The program status word is required. Program status word gives the status of the previous after execution of the previous instruction. The status will be present in the processor status register or the program status word PSW. Program status word we call it as. It will contain the data such as sign flag, zero flag, carry flags, all those flags that are supported by the particular processor are present in the or stored in the program status word, and this the status of the program status word is required for the next instruction to execute. For example, we have some instruction that is add, then we will have jump if no carry. We will have let us assume we have two instructions, add and jump if no carry. If suppose the interrupt occurs at the instruction add, now what happens, the interrupt this the processor will complete the execution of add instruction, will complete the execution of add instruction, and it switches over to the interrupt service routine. It executes the task and comes back to the this particular instruction, because this is the next instruction that has to be executed in the main program. Now if it is jump if no carry, if this instruction has to be executed, then the um, previous program status word has to be saved, because when it goes to the when after interrupt it goes to the service routine, right? In the service routine, there will be add instruction, there will be subtract instruction, there will be some other instructions which affects the program status word. So when it returns back, the program status word what you have currently is different as compared to the previous program status word before the interrupt occurs. So we need to store this program status word so that it will be used when the next instruction in the main program is executed. This is why we need to store the program status word along with the program counter. A program counter will hold the address of the this particular instruction. These are the two critical data that are required in most of the modern processors. The IO devices requests an interrupt by activating a bus line called the interrupt request. See, whenever there is a processor which has a single pin, it can serve the interrupt devices, or it can serve n devices. A single pin of a single IO can process multiple interrupt devices or multiple devices using the interrupt. The most computers are likely to have several IO devices than that can request an interrupt. A single interrupt request line may be used to serve a device as depicted in figure. That means there may be n devices that can be uh, processed by a single pin. So here uh, this can be performed by having a external circuitry that or the hardware that is used to manage the resources. Here it is done using either a special gates known as the open collector and the open drain are used to drive the switch to ground, that is open when the gate input is 0. So we have the open drain, we have open drain or open source devices. So in that case you have a gate. When the gate is 0, it is grounded, that is this pin is grounded. When the gate is when INTR is 0, when it becomes 1, this will be connected, the switch internal switch turns on and will be connected to the processor. By this way multiple devices or the n devices can be connected using a single pin, and If you may have a feeling that if two devices enable at a time, there is a priority on based on which it will be the interrupts are served. There is a priority. The interrupts with the higher priority will be served first, whereas the interrupt with the lower priority has to wait until the higher priority task are completed. This is about the interrupt hardware. In this slide, we will discuss about the enabling and the disabling of the interrupt. So sometimes, for example, if we have, if we let us assume that we have several interrupts. We have several interrupts. One of them is connected to the print. So there may not be a situation, there will be a situation that in most of the computer systems it will most of the times it will not have anything to print. It will not only when one document has to be printed, it can be printed, and rest of the time there is nothing to print. In such cases, the interrupts from the printer can be disabled. For example, if this is the pin that is connected to the printer to check for the interrupts, only when there is something to be printed, then this has to be enabled. Rest of the times it can be disabled. So the arrival of the interrupt request from the external devices causes the processor to suspend the execution of one program and start the execution of another. That we know that when the interrupt occurs, the main program gets suspended and the service is given to the interrupt. There may be chances that even though there may be some technical glitch, or there will be an interrupt occurring at one particular point by the printer, even though there is nothing to print. So such undesired states has to be avoided. This can be avoided only by the processor, by only when there is something to print, then the interrupt pin that corresponds to print has to be enabled. Rest of the times it has to be disabled.